School of Physics. So my work is broadly on terahertz spectroscopy and imaging. But today's lecture, I'm going to present on machine learning classifications of explosives using terahertz spectroscopy data. So before going to that machine learning part, let's first discuss with what is terahertz radiation and why it is so important. What extra benefits does it give? As in the morning session, Professor Manu sir has already shown you visible part of the spectrum, which he used to exploit the Raman spectroscopy, laser-induced breakdown spectroscopy, and another aspects of visible part of the light. If you consider electromagnetic spectrum, you have a broad range of spectrum from gamma ray to radio waves. Gamma rays highly energetic, radio waves not that thing. But each part of a spectrum has a unique property, which we use in different application. Similarly, we have terahertz radiation. So, terahertz radiation lies between microwave and far infrared. For a long time, there is a gap. People don't know how to generate a terahertz radiation. On the other side, you have a sources of generating X-rays, gamma rays, microwaves, radio waves, everything. But terahertz gap, it is not there. So there is officially people call it as a terahertz gap. So after the invention of lasers, people started understanding how to generate the terahertz radiation. Now, okay, we have generated some part of electromagnetic radiation. What is the use of it? Let's consider first that. First thing is, terahertz radiation penetrates through most of the materials, just like X-rays. You have a commercial application of that thing. You can use the X-rays in what you call security screening, medical imaging, all those things. Similarly, terahertz also can penetrate through lot of the materials like cloth, wood, paper, everything. And most beautiful part to separate terahertz radiation from the X-rays is that it's low photon energy. You can see here, it's hardly 4 milli electron volts. When you take a X-ray, it's in a kilo electron volts. 6 orders of different. Continuous use of X-rays will damage your tissues or else your electronic goods, whatever you are using it. Whether when it comes to terahertz, there is no side effect, there are no damages. That's first application. Now second thing is many physical properties. Yeah. When terahertz radiation interacts with the material, let's say any material, what it is going to do? What information we can get from the terahertz spectroscopy? First thing is low frequency vibrations. Many biological molecules or organic molecules have their signature prints in low frequency vibrations. That things you can extract through either Raman or terahertz. But terahertz give much more information compared to the Raman. Next thing is crystalline vibrations. Whether a solid, when you generally see a material transform from solid to liquid, there is a phase transition. Even that phase transition can be studied through terahertz. Next thing is hydrogen bonding and stretching. Liquids, as you know, water is 70% of a body, or it is considered major element in our earth. But how water behaves at low frequency vibrations, how it demonstrates at certain energies, all that thing can be studied without causing any damage to the samples. That's the beauty of the terahertz. Now, moving aside, as I said, we have a problem in generating terahertz. So how did we overcome that problem? And what are the methods of generating terahertz radiation? Yeah. This we call as a photoconductive antenna. So now the substrate material, base material is made up of semiconductor material, gallium arsenide, and it is connected, it is biased with the metallic electrodes. The purpose of this design is that you have to ignite or incident your femtosecond laser onto that gap. The gap which you are seeing over here is a gap. We call the band gap, electron gap. On that you will incident a femtosecond laser. That femtosecond laser will excite the electrons on the substrate, semiconductor gallium arsenide. Now the beauty is that the femtosecond laser, which is the order of 10 to the power of -15 picoseconds, this when ignite that material, the electrons, free electrons which are generated will excite, and once again after some time it will come back to the ground state. Now this excitation and de-excitation should be in the order of picosecond. When we call it a terahertz, 10 to the power of 12 frequency. When you convert it to a time, it's a picosecond. Now you are choosing a material such that whose excitation and de-excitation times are in order of picosecond. When an electron excites and de-excites, it emits an electromagnetic radiation. That electromagnetic radiation results in a generation of terahertz. So for this process, you need a femtosecond laser and a material whose what you call carrier dynamics, we call it as a carrier dynamics, excitation and de-excitation, or in the order of 10 power 12, and a femtosecond pulse which has an energy to knock these electrons into the excitation stage. That is the two basic principles. Until the invention of the lasers, this method was not possible. After the invention of laser, we have this method to generate a broadband terahertz pulse. Now, one more thing before going, when I am saying a laser, generally we have a handheld diode lasers, helium neon lasers and cutting lasers. For this generation part, we use a femtosecond amplifiers which has much high power, order of 10 power minus 15 space width, all this. One coolest thing about the femtosecond laser is that you can study the time period is such small that you can study the excitation dynamics, or what you call material behavior, all those things. And one more interesting thing which I find is, how many of you seen Star Wars? All of you. Lightsaber? Star Wars lightsaber.
Yes.
You can create that with femtosecond laser. Only one mirror is enough. But the worst part is we can't carry it. It will be like this much size, always cooling system need to be there. And that is the good part. Many more experiments like destructive, whether you want to study the constructive experiments, you have a femtosecond application. Destructive experiments like drone striking of the drones, large distance targeting, all those things can be done with a femtosecond laser. And that femtosecond laser has already got a Nobel Prize in around 1980s. Now there is an advanced version of this, the attosecond laser, which got a Nobel Prize this year. Now, how actually we generate the terahertz? This is a femtosecond laser. Now we are generating a pulse and we are dividing the pulse into two parts. One is for the pump and for the probe. Pump is the energy, you take the beam and split some part of the energy into, for the generation of terahertz, you can see this part goes and hit the emitter. So from this emitter you are getting a terahertz radiation, and you have a sensor and you have a probe beam. I will explain why this probe beam is split and what is the role of that probe beam. And you have a probe beam which connects to the sensor. This is the typical terahertz pulse, you get it. So this is a terahertz pulse you generate. It will be order of the picosecond. When you do a Fourier transform, you get in a frequency domain. So we convert it in a frequency domain in order to get a spectral information. The first thing is that this is a part of invisible radiation. Our science is saying that if you do this process, you are generating a terahertz, but you don't know how much it is generated or it is generating at all. Now how do I know whether terahertz is generated or noise is coming, or whether if it is generated, how much intensity is coming? So that's why we split a probe into this. Now how do we detect a terahertz radiation? Now this is the terahertz pulse. After the generation, we send the terahertz pulse without a sample. In the absence of the sample, the terahertz pulse, in the absence of the terahertz pulse, the probe pulse which we have split, let us assume this pulse is not there. This is the probe pulse. This probe pulse travels through the electro-optic crystal after the quarter wave plate, Wollaston prism, balanced photodiode. Each optical component has its particular unique response here. So when a normal optical pulse travels, its polarization is same. It's vertical, either vertical or horizontal. When it comes to lambda by 4 plate, it turns into circular polarization. Now circular polarization has both horizontal component and vertical component. When it is a circular polarization, both horizontal and vertical components are same. Now after traveling to the Wollaston prism, this will split the circular polarization into horizontal and vertical. Because they are both are same, this balanced photodiode detects two components, one is horizontal, one is vertical. Their intensities are same and the output which you get from the balanced photodiode is 0. One is subtracting, x is subtracting minus y. So this minus this does is subtraction basically. So because of this circularity, you are getting equal intensities of polarization. In the detector, you are not going to detect anything. Now, in the presence of the terahertz, your same optical pulse is converted into an elliptical pulse. This elliptical pulse, when you split into once again, the horizontal polarization and vertical polarization has different magnitudes. Now, when that goes into the balanced photodiode, those intensities are not same. So you will get a difference, a trace of the electric field. Now, this phenomena is occurring only because of the presence of terahertz. Because this entire process is called electro-optic sampling.
So this is a one law of optical computer, how it is done, selection of the polarization.
Here simply it has shown sensor, but you have built a different setup for that thing. Yeah. Now coming to, we have a terahertz radiation. Now what are the applications of the terahertz radiation? What are the actual applications? First thing, charge carrier dynamics. Now we are entering into the digital world. All our smartphones, semiconductor devices, everything is coming faster rate. But in order to look into that, what are the parameters which makes a metal or a material useful for making a chip or a component? What are all these parameters? First is conductivity, lifetime dynamics, carrier dynamics. One of the applications of terahertz radiation is that you can characterize the charge carrier dynamics so that you can predict whether this material is useful for production. Let's say now we are in the silicon age, semiconductor. And now they have also come across the graphene devices also. They are also predicting that graphene is a feasible material for the futuristic application. Likewise, there are a lot of materials which are synthesized across, which can be of potential applications in the futuristic devices that can be monitored with the terahertz radiation. Next thing is pharmaceutical characterization. You have different pharmaceutical products. One of the applications of terahertz is that it's spectroscopy. Through spectroscopy, you can characterize the pharmaceutical products, whether it is dated, outdated, or whether it's power is there or not, efficacy, that thing. One more thing is terahertz communication. Now we are in the 4th generation of communication. We are expecting the 5th generation. Already research work is going on terahertz communication. It will be 6G communication. Internet's bandwidth speeds, communications, or all this will be increased. And one of the beautiful applications is the terahertz imaging. Because it can penetrate through the material, it can be used in security application, and it has low because of its non-destructive technique, you can do the biological imaging also. People are using terahertz radiations to study the behavior of cancer, how cancer tissues are growing, how they are controlled, what is the process. All these things can be studied. The rest of the things are quality control and mechanical measurement. You can do that. Before going to that, we have this many advantages in terahertz, but one of the major disadvantages in the terahertz is that it is susceptible to the water. If you have a water vapor or water liquid species, most of the terahertz radiation is absorbed. That is a major challenge when it comes to communication, biology, terahertz imaging, because in both the situation, in our body, lot of liquids are water. 90% you can carry about. When it comes to terahertz communication, atmosphere is filled with water vapor. That is the two hindrance we are getting in progressing these parts. Now this is the basic of terahertz. Now we will further proceed with the terahertz spectroscopy.